Okay, I hope it is clear now. Okay, I hope everything is clear now. If there is a problem, and I'm sorry for that. So if X is a, I'll read this one. Let X be a locally compact Hausdorff topological space, which is not compact. One more fact is that is not compact, and then there exists a compact Hausdorff topological space X cap, Hausdorff topological space X cap, and a map I from X to X cap such that X minus Ix is singleton set, I is a continuous map, and Ix is an open set in X cap, and Ix is dense in X cap. Then this particular set, this particular compact Hausdorff space, then X cap, this particular compact, then this compact and Hausdorff space is called one-point compactification. One-point compactification of X, right? But note that here, whatever I have taken, X is not compact. Okay, if X is compact, and if I do the same thing, what will happen? That I will discuss just after this. So here, X is the resultant set is a compact and Hausdorff topological space. Okay, so this is one point, and that is unique, and this is unique in the following sense. What is the uniqueness? Let P be a compact Hausdorff topological space, compact Hausdorff topological space which contains X. That means there exists J from X to T, an inclusion such that J from X to Jx is homeomorphism. Homeomorphism means this is bijective continuous, that J is bijective continuous map, and the inverse is also continuous map. Inverse also continuous. That means in particular, if inverse is also continuous, particular Jx is open in T. So already here what I have, so that means this thing is giving me that J is a continuous, J from X to Jx is homeomorphism, okay, and Jx is open in X cap. All this thing is there, okay, this thing is there. But here what I am taken, that let T be a compact topological Hausdorff topological space for which X, which contains X and T minus Jx, that is a singleton set. Then T is homeomorphic to the one point compactification, to the one point compactification of X. Okay, one point compactification of X, namely X cap. That is what. So what I have seen, what I've done, that if I take X is a locally compact topological space, which is locally compact Hausdorff topological space, which is not compact. So in that situation, we can get a topological space X cap, for which I from X to X, there exists a map I from X to X cap, such that this four main point, that is X cap minus Ix, will be a singleton set. I will be continuous function, and Ix will be open dense subset in X cap. But what I am saying here is that so that one point compactification is unique in the sense that if there exists another Hausdorff compact topological space T, for which contains J, that means there exists a continuous function J from X to T, such that J from X to Tx, X to Jx is uh, J from X to Dx, such that J from X to Dx, sorry, J from X to Jx, which is homeomorphism. That means that is continuous, and Jx is also open. Jx is also open, and if T minus Jx is singleton set, if it addition T minus Jx singleton set, that means then this is homeomorphic. Okay, this is homeomorphic. So that is one fact is that. So if you note that here I have not taken that Jx, here I have written that Jx is open in X cap, right? But I have not written Jx is dense or not. Okay. So if I take locally compact topological Hausdorff topological space and do this process, then automatically Jx will be dense. Okay. Now if X is compact Hausdorff topological space, compact Hausdorff topological space. Okay, just before this, the so you can here what I will write, the construction of X cap. X cap, basically how this X cap was constructed, that I will just write. X cap is equals to X disjoint union of a single point P naught. Okay, and the open sets are only two type. Open sets or topology, open sets of X cap are of the type of the form. First, if X is a subset, U is a subset of A, U belongs to the tau of X cap or topology. If okay, so basically what I am just trying to say, for open set, a subset U subset of X cap is an open set if it satisfies any one of the, if it satisfies in one of the following conditions. A, if U is subset of X, U is subset of X cap, and X cap is X union a single point. So that means if U can be subset of X, if U is subset of X, then U is open in X tau. U is open in old topology. Okay, X. B, if P naught, if U is not subset of X naught, that means if P naught should be in U, P naught, then X cap minus U is an subset of X, is a compact is a subset of, this is a subset of X, is compact in X tau. X tau is the old topology. Okay, so this is the collection. So now if I do this similar process for a, so whatever this process I have already written or tried to explain, though that is for a locally compact Hausdorff topological space, for which space is not compact. Okay, now if we take X tau be a compact topological space, be a compact topological space, and take X union or singleton P naught, define topology define a topology on X cap by the same previous process, then note that singleton set P naught is closed. Why this is closed? Closed as X subset of X cap is an open set in X, so X is X tau, I mean X as a full set X is open set in X tau, then X is open in X cap, right? P naught is closed set. And also note that P naught is an open set. Why this is open set? This is open set. P naught is open set. P naught is open set. As if you replace by P naught by U in the previous place, then what you will get? As X cap minus P naught is equals to X is compact in X tau. Okay, so if you just look at what are the open set, that was the collection, two type of collection. If two subsets of U, subsets of X cap, if that means that subset U is a subset of X cap, that means that subset may contain P naught belongs to U, or P naught may not be contained in U. So if P naught is not contained in U, then U is subset of X. Okay, U is subset of X. So in that situation, U will be open set in X cap if U was open set in X tau in all topological space. If P naught is there, then automatically X minus U, which will be a subset of U X subset of X, that is compact in X tau. Now if I take X is a topological, now if I take X is compact topological space and try to define this way, then if I take U is equals to this singleton set P naught, then this P naught set is open. Why this P naught set is open? Because if I take U equals to AX, then X is open in X tau. As X is open in X tau, X is open in the new topology of X cap. So that means U as X is open, so its complement, that is the singleton set P, that is closed. That is the first reason I am saying that P is closed. Secondly, what I am saying that if I take the singleton set P naught, this set, if I take X minus U cap here, whatever it is this way, then I will get X, and which is compact in X tau. So that means this compact in X tau. So that means by the definition in the above way, X tau, that means P naught is open in the new topological space X. That means this P naught is open and closed in X tau. Okay, that means that X cap minus this P naught, if P naught is closed, is open, P naught is open, so X minus P naught, that will be X is closed, because P naught is open, this is closed and open, this is closed and open in X cap. But the fact is that if X is closed in open, so how can we write, if you look at the previous definition when we are considering locally compact topological space, there the fact is that this Ix is dense in X. What is this Ix? Ix is actually X. So that is dense in X, means X closure is equals to X cap, right? But here what is happening, that X is closed. So X closure in, so I can write here closure of X in X cap is equals to X. Okay, so X is not dense in X cap. So what my point here is that, one point compactification of a topological space, depends on the whether that is locally compact only locally compact, but not compact, or compact. If it is compact, then the after one point compactification, the main space X may not be that need not be dense. Okay, but in locally compact topological space, if I do one point compactification, which was not compact, I mean, in a locally compact topological space which was not compact, if I do one point compactification, then that locally compact topological space will be dense, will sit in the one point compactification as dense. Okay, dense subspace. So this is the point. So X is not in X. So this is the result. So this will be used in one of the and um, one of the okay, one of the problem I will use this one. And the second fact is the important one of the important fact is that okay, I think in sorry, subspace quotient topology. Quotient topology. What quotient topology say? Quotient topology. What quotient topology says? Let X be a topological space. X tau. Let's write X tau. X comma tau be a topological space. This one be a relation, be an equivalence relation, be an equivalence relation on X. For example, on real number we can give relation like if one of them, I mean take two real number A and B, they are related if and only B minus A is even or odd, something like this. I mean, just for example I'm talking about. So X tau be a topological space, and let this particular thing is that this one is an equivalence relation on X, then these equivalence relations will um, will make an equivalence classes in X, and then X mod this is the collection of equivalence classes. Equivalence classes. Now can we give, and this is equivalence classes, then there exists a map pi from X to X mod tau by pi of X is equals to X cap. This one is equivalent classes corresponding to equivalent class corresponding to X. I mean, basically, what is equivalence class? Suppose X is any set. I am giving a relation on them, and that will make division of equivalent classes. That will make full X to divide in equivalent classes. So every element of that main set X, that will be either in one of the exactly in one of the equivalent classes. So that is the equivalent classes where X belongs. Okay, that is the equivalent classes where X belongs. So equivalent correspond to X. There is a map pi, okay, and that is surjective. And this map and pi is surjective. This is automatically because every equivalent classes in X mod tau. This is the collection of equivalent classes. Every equivalent classes obviously correspond to some point. That is natural because every equivalent classes contain some point of them point. Okay, surjective. So now question is, can we give a topology? So we know that X has a topology, right? Now I want to give a topology on X mod this tilde, for which we will get pi is continuous with also some extra point. Can we give a topology on X mod tau such that it will satisfy the following conditions. First one is that pi is continuous. Second one is that for every other topological space y tau y and a continuous map f from X to Y such that f is constant on each equivalent classes of X, each equivalent classes of X must factors continuously, must factors through X mod cap continuously. That means, suppose I have X and this X mod tau, X mod so I want to give a topology tau. Here I will write X tau X, X tau X. So suppose I want to give a topology here in X, this is pi, and suppose Y is another topological space which has a topology, right? And this F is a function. F has a special property that F is constant on equivalent classes of X. Okay. So in that situation, so can we give a map? So in that situation, F should be factored through X mod this tilde. That means there should exist a map, unique map. There should exist a F naught such that F naught is continuous, and F naught compose pi is equals to F. That is what means factors. Okay, and in the topology, and there exists a topology, and these two are the condition. Question is whether can we give a topology on X mod this tilde such that it will satisfy these two conditions. Okay, so and the answer is yeah, we can give such topology on X mod tilde called quotient topology, and quotient topology, what is that quotient topology? That is equals to, that means collection of open set. U is subset of X mod tilde, that is the quotient space, if and only such that all those subset will be there for which pi inverse U is open in X, open in X tau X, right? This is the thing. This is the topology. Topology is nothing but collection of open sets. So what are the open set in X mod this tilde? What are the open set? Now all those open set for which this pi inverse, pi map is always defined. For a set X and its quotient, pi map is always defined. That is surjective map. So every open set, if a set will be open in X tau, if the inverse image of pi is open in X. So basically what I just trying to explain is that a set is always, for a topological space X, there always we can give this one is pi is surjective. So a set U is subset of X. This is open in if pi inverse of U is open in X. That is the condition. Okay, pi inverse of U is open in X. That is the asking condition. So now. So this is called quotient topology. Okay, this is called quotient topology given by this. Okay, I think I don't need any theorem right now. I think I can start for the problems, and if I need, I think maybe I need one more theorem. Otherwise, I don't need theorem. Okay, so now first question. So assignment 7. First question. What is the first question? First question is that if is a homeomorphism of locally compact Hausdorff topological space, then this is not, yeah. So this was the first question. So question is that if F from X to Y be a homeomorphism, if F from X to Y be a homeomorphism of locally compact Hausdorff topological space, then F induces a homeomorphism from one-point compactification of X to one-point compactification of X. So that is the question. Okay, so I use that universal property type of things. Okay, if you look at, let's take X, let X cap be the one-point compactification, be the one-point compactification Okay, so let's start with some exact term. So let x cap is equals to x disjoint union of p naught is the 1 point compactification 1 point compactification of x. Okay, x tau locally compact of Hausdorff topological space x, and then there exists I from x to x cap such that I is continuous, Ix is open and dense in x cap, and x cap minus Ix, that is equals to singleton set P naught. Okay. Similarly, we can get y cap, which is equals to y disjoint union of q naught comma I from y to j from y to y cap as 1 point compactification 1 point compactification of y. Okay, now let's x to y be the let f be the homomorphism from x to y. Let f from x to y be a homeomorphism, that means bijective plus f and f inverse are continuous. This is the homeomorphism, and then look at this diagram. This is the f, that is homeomorphism, that is bijective, that means f inverse is also continuous and f, all those things is there. And suppose this is the map J which maps to a y cap. Okay, now then J compose f from x to y cap be a this map be J from x to y cap be a continuous map, right? Continuous map, and note that j of f of x is equals to y. There is no problem with this, and j of y is dense with open dense set in j of y is open dense in y cap, right? That was the definition of the 1 point compactification of y, and moreover this y cap minus j of y, that is equals to singleton set q naught. That means if I take this j naught f function, that will satisfy what is the condition, that j naught f of x, that is equals to y, and y cap minus j naught f y, this one is equals to the singleton set q naught, and this is j naught f x, not this one, that means these two factors. Okay, let me write it clearly. That means j naught f x is open and dense in y cap, and y cap minus j naught f of x, that is a singleton set q naught, and this j naught f from x to j of x is an homeomorphism. Now if you recall the theorem defined in above, in place of t, if we replace y dash, then there exists a unique continuous map j compose f tilde, that I will write j compose f tilde from x from y cap to x cap Okay, such that the x cap such that J compose F tilde at the point of Y. What will be that one? That one will be same with J compose F. I think, okay. That one will be J compose F tilde Y is equals to J compose F of Y. Okay. J compose F of Y and J compose F tilde all other point in y cap. Okay, in y cap what are the point? In y cap points are like y. Okay, this will change because this will be changed. Okay, J compose F tilde of I of J of Y, that one will be like F tilde J of Y, that one will be like J compose F of Y, F of J compose F for the function from this one, and this function will be like, oh, this will be I of, no, this is not I of Y, F of Y, I think. Yeah, I of F1. Just a minute. J compose F tilde of J of Y. Okay. Just to let me diagram the door. Let x to y is F, and from this is J. This is J y cap. Suppose this is the x cap, we have I. Okay. This is the 1-point compactification. Okay. The 1-point compactification of x. Okay. Now we can give a map. There exists a map that is J compose F tilde, such that J compose F tilde will a point in J compose. Okay, the points in Y are like, okay, got it. So points in Y are like, so that will be something like J of Y, not J of Y. Okay, the points in Y cap are something like J compose F of Y, that will be F of X. This is a this is equals to I of X, and J compose F tilde. If you note that this Fx for all x, it will be like, now only point left is the Q naught, that will be P naught. That means, I mean, basically what my point here is that these x and y are homeomorphic. Okay, so for every point here, y has 1 point, and this y cap is basically y with the point Q naught. Okay, so and there is also for x, the map is also like, here is also x cap is equals to x union of P naught, right? So now for every element x, there is a point in y. Okay. Similarly, okay. Now if I take point in y cap, that point will be either from y or q naught. If it is q naught, I will map it to the P naught. If it is not q naught, that means point coming from y. So that y must be f inverse. So if I take an element y from capital Y, so that y will be f inverse of some x. Okay, so now I will take that, okay, or I can write y is equals to f of capital X. So every element in y can be written of f of x, right, for some x. So for any x belongs to capital X, we can write the point here we can write point here, y cap is equals to j of f of x with the union of q naught. So that is what I have written. J of f of x. Okay, that is what. J of f of x with the union of q naught. Yeah, so I think this is correct. Yeah. So this is bijective. Okay, this is bijective and continuous. That was the universal type property. And that means this J naught f tilde is bijective and continuous. Okay. But note that Note that y cap is compact and x cap is housed off. That means J compose F tilde is an bijective continuous function, is a bijective continuous map from a compact space to a housed up space, compact space to a housed up space, that is imply that J compose F tilde is a homeomorphism. That is already it is said in lecture, and I already mentioned that if there is a bijective continuous function from a compact space to a housed up topological space, then that is homeomorphism. Okay, homeomorphism that implies that x cap and y cap are homeomorphic. So here option A is true. So for two locally compact topological space x and y, for two homeomorphic locally compact topological space x and y, homeomorphic locally compact topological space x and y, their one point compactification is also one point compactification is also homeomorphic. Okay, so this is the first question. If there is any problem, you can ask. I'm trying to do the next problem. Which one is the 1 point compactification of real number? So that already I discussed. Still I will discuss a little bit, just to so I will discuss here I will discuss a little bit more. We will prove that here what it is asked, 1 point compactification of real number are. Prove that 1 point compactification of r to the power n is Sn. Okay, let's talk how Sn. What is the Sn? Sn is x1, x2, xn plus 1 coming from Rn plus 1 such that summation of xi square I equals to 1 to n plus 1 is equals to 1. This is the Sn. Okay, we know this is subset of r to the power n plus 1, right? We know Sn minus north pole, that north pole, and take n is equals to the north pole, something like n is equals to 1, 0, 0, that is the last point, that is the north pole, that is sitting inside Sn. Okay, now we know this is not capital N, this is the small n, Sn. We know that Sn minus this north pole, this one to R phi, stereographic projection, we know the stereographic projection phi, we know the stereographic projection phi from Sn to n, Sn minus n to R is a homeomorphism. Okay, homeomorphism r to the power n, this is a homeomorphism. So phi inverse from Rn to Sn minus this north pole is also a homeomorphism. Okay, and this Sn minus this north pole, this is sitting inside S of n, right? Okay, now note that Sn is compact and housed off. Okay, now if I take Rn to Sn minus n, this set to the this one is inclusion, this is the J, this is Sn, then note that J compose phi inverse. If I take J compose phi inverse as a map, J compose phi inverse is from Rn to Sn, then J compose phi inverse is continuous, then this is continuous. J compose phi inverse of Rn is opened and dense in Sn, and J compose phi inverse Rn, if I subtract it from Sn, then I will get the singleton set n. Okay, so that means what is the fact is that means here whatever the property of Sn is, that we can give, that means we can give a map, that means we can give a map G from Sn, we can give a map G from Rn to Sn such that G of G is continuous, such that G from Rn to G of Rn is homeomorphism, and and GRn is open and then dense in Sn. That means Sn is one point compactification or homeomorphic to one point compactification, one point compactification of Rn. So basically, what is the one point compactification of Rn? That is, I have to find a set Y such that Rn is sitting inside Y, and I can give a map from Rn to Y, J, give a map G. Here G is basically this J composed phi inverse. We can give a map G from Rn to Y. We can suppose I have to the Rn is sitting inside Y, and I can give a map G such that G should be from Rn to G of Rn is homeomorphic, and that homeomorphic and the image GRn is open and dense in the set Y. Okay, and Y minus that is singleton set. And Sn minus G of Rn is equals to singleton set. So that's these three factors will give the discompactification. So in particular S1 is one point compactification of R. That will give the second question. This one. So all other will not be. Okay. So here if you note that two fact will be there. Okay, let's first prove those one. So okay, now I'm going to question 3. What is the question 3? That which one of the following is homomorphic to the one point compactification of the set of integers? Okay. This is the question number 3. Which one of the following is which one of the following is homomorphic to one point compactification of the set of integers? Okay, we know set of Z is homeomorphic to the set A is equals to 1 by n belongs to Z, and n greater than 0. N greater than 0. as they are two countable sets. As they are two countable infinite sets. They are two countable infinite sets. So basically my point is that for two countable infinite sets we can give a bijective continuous function, countable infinite, and as Z and A has discrete topology as subspace topology. As a subspace topology of Z and A are discrete topology. That is the one. And okay, so I will better to clear rightly. As Z and A are countably infinite, then there exists a bijection f from Z to A. We can even define this bijection. How this bijection can be defined? Suppose I have a integer n. How this bijection is defined? Okay, I can give this bijection from A to Z. How? F of 1 by n, that will be depends on the two facts. If n is even, then it will be like n by 2. It will be minus n minus 1 by 2 if n is odd. So using this one, this is a bijection. This one is a bijection from A to Z. So then Z are countable infinite, there is a bijection. Okay. And the standard topology of Z and A as subspace topology are discrete topology. So any function f from A to Z, if I have discrete topology on the left hand side, suppose I have discrete topology on A, then f will be continuous. So now f is bijection. So f inverse, f inverse will be from Z to A, but Z is also have discrete topology. Okay, so then f inverse will be continuous. So f is bijective and continuous. That means f is a homeomorphism. So f from A to Z is a homeomorphism. So f from A to Z is homeomorphism. Okay. So now we have proved in first problem. What is the first problem? That if x and y are two homomorphism of locally compact Hausdorff topological space, and f induces a homeomorphism from one point compactification of x to one point compactification of y. So that means if x and y are two locally compact Hausdorff topological space, now as A and Z are locally compact Hausdorff as are locally compact Hausdorff topological space are locally compact Hausdorff topological space, and f from A to Z is a homeomorphism, then there are one point compactification A cap and Z cap are homeomorphic. Okay, now so that means one point compactification of Z is homeomorphic to A cap. That is, A cap is one point compactification of A. So a cap is 1 point compactification. If we recall what was a cap, that 1 by n such that n belongs to integer and n is greater than 0. So this was the a. So now a cap, if you look at this set, a cap is compact. A cap, what was the a cap? And a cap is, and basically a cap is just 1 by n, n belongs to z, n greater than 0, union the singleton set 0. So this is closed and bounded, closed and bounded in standard topology of R. This set is closed and bounded. Why this set is closed and bounded? You can only possible limit point of the set is A is 0. So that set is actually basically closure of A is A cap. Okay. So that means this is compact. That means A cap is compact and housed off. A cap is subset of R and R is housed up. That means A cap will be also housed up. That is, there will not be any problem. So A cap is housed up and compact. So A cap. So now A cap is housed up and compact. So to show A cap is 1 point compactification. Okay, so this set is okay. So I have to find what is A cap. Okay, that is what. So A was this. Okay, so take this one. A cap is defined like this way, or I can take this set is suppose M. M is the let. Okay, then okay, just a minute. Define A cap is equal to this. To show A cap is 1 point compactification of A, only need to prove that A cap okay. So let's take one compactification of A. So let's take J from A to A cap. Just identity map. J of A is equals to for all A belongs to capital A. Then J from, then this is very much clear. J from A to J of A is homeomorphism. First fact is this, and second fact is homeomorphism. First fact is this, and A cap minus J of A, that is a singleton set 0, is a singleton set. That means A cap and J of A is open and dense in A cap. Okay, that means A is, why it is dense? Because the dense means closure should be same, and you can look at the closure as closure of A is equals to A cap. Just A contains a sequence 1 by n. So if I want to get what is the closure of A, if A, that should contain the limit point of that particular that should contain the limit point of the particular set A. So A set contains 1 by n. Okay. So what is the limit point? That is 0, and A cap contains 0. That means A closure is actually A cap. Okay. Open and dense in A. So that gives the denseness. Okay. Open and dense in A. So that means A cap is 1 point compactification, 1 point compactification of A. That means this A cap, which is equals to 1 by n, n belongs, n is a integer, and n is positive with union of 0, and n positive with union 0. This set is 1 point compactification of Z, because what we have proved that one point compactification of A and Z are same. Okay, so that means, and one point compactification of A, what I have proved, that is actually A cap. So that means this A cap means the set with 0. So that means this is the one point compactification of Z. So that means this gives the one point compactification. This one is the correct option. S1 is not the correct option, and because they are not homeomorphic, so that's why they are not correct. This one union of Z and a point. This is not correct. Why this is not correct? This one union of Z and a point. This union of Z and a point is not correct because their topology is not defined. Okay, so that's why this is not correct. S1 will not be. S1 will not be because S1 is something like connected. I think you cannot give from Z to, I mean, Z one point compactification of, basically this set is one point compactification, that 0 union 1 by n, and this set is not homeomorphic to the set S1. And if I give another topology of Z and a point, if I give here this union of Z and a point by if I give here the what is called trivial topology, so trivial topology, if we give trivial topology, this will not satisfy. Okay, if we give trivial topology on Z union a point, disjoint union a point, topology to the disjoint union to disjoint union of Z and a point, then it will not be homeomorphic to the set of option C. So this is not homeomorphic. So at least one point compactification are homeomorphic. That I have proved earlier in today's lecture. So that's why this is not one point compactification. Only one point compactification is the option C. Okay. Now go to the next question. What is the next question? If there is any doubt, you can ask. Otherwise, I am going to automatically to the next question. What is the one point compactification of the set? What is the one point compactification of the set? Open 0 to close interval 1. What is the one point compactification of this set? And this will be like this one. Why other is not? Here is two. Here I will mention the fact here. One point compactification, the other will not be. That automatically other will not be, because one point compactification will be homeomorphic to each other, right? So one point, the set 0 1, the close interval 0 1 is one point compactification of 0 1. Why? 0 is open and 1 is closed. Basically this should be written carefully, because this is the thing. Of 0 1, this is the thing. Why? Because as if we can give J from 0 1 to 0 1 close interval identity map 0 of x is equals to x is a homeomorphism, is a continuous map, and J of 0 1 close interval, this one, okay, sorry, this will not be J from this is equals to 0 1 is homeomorphism, and 0 1, if we subtract from these two 0 1 this set, what will be? This will contain on the singleton set this one. Okay, first factor is, so 4 factor is there. First one is that there should exist from J to X cap which is continuous. Second factor is that x cap minus j of x will be singleton set, and third factor is that j of x is open, and fourth factor is that j of x is dense. So these are the four factors. So basically, okay, basically here you can write, so to get 1-point compactification, okay, so basically the criteria for 1-point compactification, you can write here this one, criterion of finding 1-point compactification, finding 1-point compactification. How one can find? We need to find a set, a compact Hausdorff space, a compact plus Hausdorff space x cap such, and a map, and a continuous map, and a continuous map j from x to x cap such that first one is x cap minus j of x is singleton set. This should be singleton set. Okay, this is for of a locally compact Hausdorff space. Okay, this criteria is for locally compact Hausdorff space. X minus jx is singleton set. First is x minus j is singleton set. Second is that j of x is open and dense in x cap. Okay, open and dense in x cap. I think this is all. I have already continued. So this is the criteria for 1-point competition of a locally compact Hausdorff space. Criteria of 1-point compactification of a locally compact Hausdorff space X. So what we have to find? We have to find a compact plus Hausdorff. Okay, we have to find a compact and Hausdorff space x cap and a continuous map J from x to x cap such that x cap minus jx is singleton set and jx is open and dense. Here, what is the note here is that note that x needs to be locally compact but not compact. If x is compact, then j of x need not be dense in x cap. I have to mention this one because this was the confusion may arise. Okay, so here what I am taking, that I am taking is, this one is at the 0-1 close interval as the x cap. Okay, 0-1 as the x cap, and this j is defined like this way, and this is singleton set first, and this 0-1 is, note that 0-1 is locally compact space. 0-1 is locally compact, clearly not compact, locally compact and not compact. So two facts. First, whether I have to check whether that is locally compact but not compact, or just compact but just compact. Okay, this is not compact, that is locally compact. Why this is not compact? Because that is subset of R. In R, one set is compact if and only if it is closed and bounded. Okay, so that means here 0-1 is not closed because the limit point 0 is not there. Okay, so that's why as 0-1 is not closed in R. So this is the reason that this is locally compact. Okay. So now this is singleton set, and clearly the singleton set 1 as the singleton set 1 not 1 as a singleton set 0. This is 0. Sorry. What I'm doing. 0 as the singleton set 0 is closed, as a singleton set 0 is uh, closed in the okay, the new inter this closed in this 0 1, that means the 0 1 j of 0 1, which is equals to 0 1, is open in 0 to 1 this set. Note that here one fact there note that 0 open 1 closed is not open in R but open in 0 1 with subspace topology. Okay, so in subspace topology, this 0 1 side 0 and 1 closed, that one is open in 0 close interval 0 1, but this is not open in the main topology of R. Okay, so that should be known. So that is open, and clearly closure of 0 1 in close interval 0 1 is equals to close interval 0 1. So that means this 0 1, which is equals to j of 0 1, is open and dense in close interval 0 1. So that means close interval 0 1 is 1 point compactification of open 0 to 1 closed. Okay, so here one important fact here is that 1 point compactification of R or 0 1, because 0 1 open interval R is homeomorphic to the open interval 0 1, is given by S1. Okay, that is circle, and 1 point compactification of 0 1 or I'll just write this one: 0 closed 1 open is close interval 0 1. Okay, but it's close interval 0 1 and S1 are not homeomorphic, proved in the last class. Homeomorphic proved in last tutorial. So note that it may seems that 0 1 is, if I take open interval 0 1, it may seem that okay, close interval 0 1 is the 1 point compactification, because close interval 0 1 is the compact set containing 0 1, but no, close interval 0 1 is not 1 point compactification of the open interval 0 1. Okay, if both side is open, then close interval 0 1 is not the 1 point compactification. Okay, this is the thing anyone should care. So the 0 1 is a 1 point compactification, and clearly this is, I mean, whatever I have said, and this gives all this information, because close interval 0 1 is a 1 point compactification of the open 0 to 1 closed, and that is not homeomorphic to S1. So S1 is not 1 point compactification, and disjoint union of 0 1 and a point need not be, because suppose I can give a discrete topology on this particular 0 1 disjoint union of 0 1 and a point, and obviously none of this option is not there. Okay, so this is, if there is any problem you can ask, no problem. Otherwise, I'll go to the next problem. Now this is the next question. Okay, that is what that is already I've discussed. This is
Excuse me,
5.
sir. Sir,
Ah, yes.
sir, one point compactification of closed interval 0 for both same, sir.
Sorry, one point
Open,
compactification.
closed and closed open. Of
No,
open closed and closed open
that they are same. I mean,
for
zero
both
one.
same.
Yeah, zero. I mean, zero open and one closed. Okay, or
Yes, sir.
zero closed, one open. They are both same, and that is closed interval 0, 1. Okay,
0, 0, 1. Okay, okay, sir.
because the main fact is that one point compactification. Suppose I have a locally compact topological space X. You want to find one point compactification. That means X cap. So you have to find a map from X to X cap and a map J such that X cap minus J of X is a singleton set and
Singleton
Jx
point.
is
Yes,
sitting
sir.
singleton pod, and that is sitting inside in X cap as a open and dense set. Okay, so you can do this thing with close interval 0, 1. Okay, but note that that is very important. 0, 1. If I take open interval 0, 1, the one point
Oh,
compactification is not close interval 0, 1. Then one point compactification is
so
S1.
okay.
Yeah,
What about closed interval 0, 1?
that is already compact. Okay, so there is a
Oh,
question. The one point compactification. Oh, okay, just let me clear that will come in question number 8. One point
okay,
compactification of
okay.
a locally compact topological space is just adding a point, right? But if you want one point compactification of a compact space, that's just adding a point and define a topology like define in notes, share notes, or in the early, I mean just first initial first 10 minutes I think I have discussed that how to do the one point compactification. If I take compact set already, 0, 1 closed interval, this is already compact, right? And
Yes,
its
sir.
one point compactification is like 0, 1 union a disjoint point, some P naught. But
Yes,
in
sir.
this particular situation, the J from 0, 1 closed interval to the one point compactification, now this is the one point compactification. Okay, I don't know whether you are able to see my board where I am doing. That is, suppose 0, 1 to 0, 1 close interval union a singleton point P is coming from outside of close interval 0, 1, right? So this is the one point compactification. I mean 0 close interval 0, 1 union a singleton point P, that is the one point compactification of the close interval 0, 1. But here the image and J is given like J of X is equals to X. Here image of close interval 0, 1 is need not be dense in this one point compactification set for when it is compact. I mean, one point compactification can be done for locally compact topological space which is not compact and a compact topological space. If it is locally compact topological space, then image should be open and dense. Okay, whatever we are doing till now. If it is compact, then denseness only be removed. Everything will be there. Is it clear?
Oh, yes, sir. Yes,
Okay, if
yes,
there
sir.
is any doubt, you can ask me. Okay, so this is the okay. So last question was that one point compactification of the one side closed or. But right now, the one point compactification of it is asked one point compactification of open interval 0, 1. We know 0, 1 is homeomorphic to R. 0, 1 is homeomorphic to R. Then one point compactification of one point compactification of 0, 1 should be homomorphic to one point compactification of R. One point compactification of R. That is by problem number 1. Problem number 1 is there if x and y two are locally compact topological space and they are homeomorphic, so their one point compactification also be homeomorphic. But one point compactification of R, one point compactification of R is S1 that I have proved. So that means 1 point compactification, 1 point compactification R of 1 point compactification of open interval 0 1 is S1. So this is the reason. And S1 is not homomorphic to closed interval 0 1, so S1 is 0 1 is not there. Disjoint union of 0 and a singleton set, so I can take 0 1 closed interval and the 0 1 open union the disjoint point is 0. So that means this will be basically this will be 0 1 open interval. So that is not even, that is also not compact. Okay, that is also not compact, and D is also not there. Okay, so not compact, not compact. This is not the compactor. This is the set. This is not 1 point compactification. Okay, so this is not 1 point compactification. I think you can stop your video, Hiral Alberma. You can stop your video. Okay, so 1 point compactification of 0 1. Hello, Hira. Hello. Just pause your video and the audio also. I mean, if it is, you are not asking anything. Please, thanks. Yeah, thank you. So 1 point compactification open interval 0 1 is S1. Why? Because 0 1 is homomorphic to closing R real number, and two locally compact topological space are homomorphic, so their 1 point compactification will also be homomorphic. So that's why 1 point compactification of 0 1 is same with S1. Okay. Now I'll go to the question number 6. I think this is the question number 6. Question number 6. What is the 1 point compactification of Bn? Okay. Let's take. We know 0 1 is homeomorphic to R. Similarly, the open interval similarly the I can say that take the set S1, not S1, this is the unit ball. I can take B2, that is equals to all those x1 comma x2 coming from the real number R, such that summation of x1 square or x2 square, not summation, x1 square x2 square less than 1. So this set is homeomorphic to R square. How I can give this set is homeomorphic to R square? I can just give this way, just to give a map from R square to B2 by sending f of x1 comma x2, that is equals to x1 by x1 square plus x2 square plus 1 comma x2 root under. I can give root under, I think. X1 squared. I think I can give this one plus 1. So check that this is the map. Check that f is bijective and continuous clearly as it is polynomial, continuous. Okay. Why this is continuous? You can note that for any point x1, x2 coming from real number R, x1 square plus x2 square plus 1, that is non-zero, always non-zero. Okay, so that is non-zero means x1, so f that is non-zero, so that means x1 comma x2 going to x1 by root under x1 square plus x2 square plus 1 is continuous. So that gives f is continuous. And bijective also can be proved. That is not a big. So f is bijective and continuous, and the inverse is also continuous. Moreover, you can look at that f is homeomorphic. Moreover, f is homeomorphism. So as f is homeomorphism, that means R square and the unit ball B2 which is equals to all x1 x2 coming from the real number r square, such that x1 square plus x2 square less than 1. Note that I am not writing equal or less than equal. This is less than 1, is homeomorphic. So 1-point compactification, 1-point compactification of B2 and R2, R to the power 2, are also homeomorphic. But 1-point compactification of 1-point compactification of R square is S2. So 1-point compactification of B2 is S2, because that is the first problem, that if x and y to locally compact houses of topological space, they are homomorphic, their 1-point compactification are homomorphic, and 1-point compactification is unique. So that means 1-point compactification of B2 and 1-point compactification of R2, R square, are same, and same means homeomorphic. So that means 1-point compactification of B2 is same with the 1-point compactification of R2, and that is S2. So this is the, so in particular I can do for n. We will do for n is equals to 2. So 1-point compactification of this Bn is S1, and this particular set closed unit ball Bn is not there because Sn is not homomorphic to this particular set. Okay, Sn is not homomorphic. Note that for option B, Sn is not homomorphic to the set x1 x2 belongs to R square, such that x1 square plus x2 square is less than is equals to, if I am not wrong, yeah, x1 square, I am doing everything for 2 and everything for n equals to 2, and all thing automatically will follow for the n equals to dn. Okay, so this is the set dn. Homomorphic is not homomorphic to d2 equals to this. This is not homomorphic to this one. Why this is not homomorphic? For example, if I take n is equals to 2, okay, this is not homomorphic. Sn, okay, S2. So why this is not homomorphic? If you look at, suppose there exists a homeomorphism A from S2 to D2. I can give you the pictorially, that is what is the S2? S2 is the this set, okay, this circle, this is the S2. Okay, no, this is S2, this circle only, not the interior region, okay. And what is the this D2? D2 is actually the closed circle. Okay, this is the closed circle, so I can write it as this with boundary, and the closed circle, this is the with boundary, this is the D2. So now if we take 2 point here, if we just remove 2 point, this one and this one, for example, I mean, let's take 2 point here, like this point is something like, and this point, and take this one is the point x, and this one is the point y. Okay, this one is the point y. Now if we remove S2 to these 2 point x and y, these 2 point x and y, what will be? This is not connected. But if there exists a homeomorphism F, if there possible a homomorphism F, so that should be bijective. So now if we remove 2 from here, so there will be corresponding removal of 2 point, any 2 point. But removing any 2 point from this closed unit ball, that does not makes it non-connected, right? I mean, my point is that if we remove 2 point from this particular space, this closed circle, suppose remove 2 points from any places. If you remove 2 points, does that make it not connected? So suppose so, but d2 is d2 below, but d2 minus f of x comma f of y is not is connected. This is connected. So f inverse will map d2 minus f of x f of y to s2 minus x comma y. That means f inverse will map a connected set to a non-connected set. That is a contradiction. So there does not exist any such homeomorphism. F from S2 to D2. So S2 and D2 are not homeomorphic. So that means D2 can't be the one-point compactification of Bn, because one-point compactification of Bn is Sn, and any other one-point compactification will be homeomorphic. So that's why. And Rn is not compact, so this way this will not hold. Okay. I hope this is clear. If there is any doubt, you can ask. Yeah. So now this is question number 7. Question number 7. Yeah. Question number 7, what it is, what is the one-point compactification of the interval 0, 1 and 2? What is the one-point compactification will be? What is the one-point compactification of 0, 1 union 2, 3? So this is I mean, this is a little difficult question, but that will be the union of two circles tangent to each other, but not any other options. Okay, first of all, not any other option. You can look at this. None of them. You can look at the none of them will satisfy the. Okay, none of them will hold. Okay, first if I prove the A, then all other will automatically hold. Let's prove the A. We know. Okay, let's take S1, S2. Let's take S1 and S2 are two circle tangent to each other, right? Tangent to each other. Tangent to each other. So basically what my point is that, suppose this is the real line, this is the point 0. So here what is that? 0 to 1, this is 1, and next is that 2 to 3, right? These are the total interval. 0 to 1 and 2 to 3. These are the total interval. Now, one-point compactification will be, how one-point compactification will be? You know, we have discussed already 0, 1, and one-point compactification of 0, 1 is S1, a circle. But I can know that S1, what is S1 we know? S1 is the circle which centered at origin, but not with any other point. But any circle in the plane, that will be homeomorphic to the S1. That is homeomorphic to the S1. Okay. So any circle in the plane is one-point compactification of the open interval 0, 1 or the real number R. Okay, I think this is clear. As any circle in R2 is homeomorphic to S1, so that is better to write this one. As any circle in R2 is homeomorphic to S1, any circle in R2 is homeomorphic to S1, then 1-point compactification of any circle in R2, then any circle in R2 is 1-point compactification of 1-point compactification of 0, 1 or real number, whatever. Okay. But the point is there, so I can change the circle. That is my point. That was what I want to make sure. Okay, now what is these two tangent, that is means that just take, I don't know whether I will be properly able to draw the circle. Yes, got it. So 1-point compactification of this one, 1-point compactification of this is the tangent point. Okay, this is the tangent point. This is the tangent point. So 1-point compactification of 0, 1 is this one, and 1-point compactification of 2, 3 is this one. So that is what how we'll construct. Okay, so um, let's do the calculation. Let take S1 and S2. This one the S1 and this is S2. Okay, let's S1 and S2 are two circle tangent to each other at the point. This is means tangent to each other. That means they will touch only a single point. Okay, this one circle will be outside of the other circle. That is not always true. This circle S2 can be inside of S1 also. That is not a problem. S2 can be, I mean, this can also happen. That there's something like this one. It is clear that just two circle, how one circle can touch other circle. Something like this can also happen. So that is my point. So so 1 point at what, at the which point they are tangent? They are tangent at the point x comma y. Then we will give, okay, then we have to give then we have to show that this set is compact, and we can give a map. That is what I just, this is question number 7. Yeah, so we can give a map. That is, then S1 union S2 minus x comma y, this is the set, is homeomorphic. I have to show this is homeomorphic to 0, 1, right? Okay. Clearly, S1 is 1-point, not clearly, such that S1 is 1-point compactification of 1-point compactification of 0, 1. S2 is 1-point compactification of 2, 3. And we can get such type of, we can get such type of S1, S2. Okay, what my point here is that 0, 1, 1-point compactification of 0, 1 is a circle S1, and 1-point compactification of the open interval 2, 3, that is again a circle S2. But S1, S2 need not be tangent to each other, right? Need not be touch each other to at a single point. But we can choose S1 and S2 such that S1 is 1-point compactification of 0, 1, and S2 is 1-point compactification of 2, 3, and they are tangent to each other at a single point x comma y. That is what my point. Okay, now that means there exists I1 from, or Ij, that is there exists I, that means I from 0, 1 to S1 such that I of 0, 1, and if I remove S1 from I0, 1, this is a singleton set xy. We can choose S1, S2 such that this will happen, and J from 2 to 3, that S2 such that S2 minus, this is S1, okay, such that S1 minus I of 0, 1, that is equals to singleton set xy. S2 minus J of 2, 3, open interval, that is equals to singleton set xy. We can choose all of this satisfy at a single time. We can choose. Okay, that is what my point. So now then give a map F from 0, 1, union 2 to 3 to S1 union S2 by F of X is equals to I of X if X is in between 0, 1 and J of X if X is in between 2 to 3. Then clearly F of this 0, 1 union 2 to 3 will always avoid the point. Then clearly then S1 union S2 minus this one is the singleton set X 0 comma Y. That's it. Then and F is continuous, I is continuous, J is continuous, F is continuous, and F from the set 0, 1 union 2 to 3 to S1 union S2 minus X and Y is a homeomorphism, and 0, 1, 2 to 3, which is equals to S1 union S2 minus XY is open and dense in S1 union S2. Why this open thing is dense thing is clear, because that is a the dense thing is clear because X comma Y. Okay, I can write it here. Open as singleton set XY is closed. So this complement is closed. So its complement is open. So its complement is open. And why dense? Because X comma Y is limit point of the set. Limit point of the set S1 union S2 minus X1. So this is the two facts. So I think this is clear. My point is that we can choose S1 and S2 to one point compactification of the open interval 0, 1 and 2, 3 such that the I can be given like that 0, 1 to S1 such that I is continuous, and J from 2, 3, 3 to X2 such that J is continuous, and I S1 minus I of 0, I of 0 1 is X comma Y, and S2 minus J of 2, 3 is equals to X comma Y, and S1 S2 are touch to each other at the single point 0, 1. Then we can get the set S1 comma S2 and remove the point X comma Y, and that then we can look at this function F this way. Then this is continuous and homeomorphism. This is not only continuous, this is homeomorphism because this is combination of I and J. I and J are homeomorphism. So I is homeomorphism from 0, 1 to S1 minus 0, S1 minus XY, and J is homeomorphism from 2, 3 to S2 minus XY. So that's why these are homeomorphism. So as they are homeomorphism, so F is also homeomorphism, and S1 minus S2 minus, so S1, and this is also S1 union S2 minus F of 0, 1 union 2 to 3 is a singleton set. Is a singleton set X and Y. So S1 and S2 are this is the one point compactification is the one point compactification of 0. I hope this is clear. If there is any doubt, you can ask. Okay. I don't know. Is there any doubt? One point compactification. I hope this is not clear. If there is any doubt, you can ask. Otherwise, I will do the next question. Yeah, this is the point. This is the question number 8. So here X is compact topological space. Then what is one point compact topology? That is disjoint union of X and a point. Okay. Here a point is not any compact set containing X, that is also not, because that would be one point compactification of a compact one point compactification of a compact set of a compact set X is X cap, which is equals to X disjoint union of the singleton set P naught, where U subset of X cap is open if either P naught U subset of X is open in X, or P naught belongs to U and X cap minus U is compact in X. That means we have just discussed few minutes ago. That means X is X, then and if I define J, if I define I from X to X cap, then X cap minus I of X is a singleton set P naught, that is for sure. I is continuous by, I will define by I of X is equals to X. Then I is homeomorphism, not only continuous. Then 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 I from X to I of X is homeomorphism, as it is bijective is clear. It is bijective because this is just identity map. Okay, bijective and continuous, and note that I maps a open set in X to an open set I of U, which is equals to U in X cap. So I is homeomorphism. So I from X to IX homeomorphism, and IX is open in X cap. But note that X cap, but IX, which equals to X, is not, this is not dense in X cap, as X is open and closed in X cap, then X closure is not equals to X, which is not equals to X cap. Okay, so that means one point compactification of a compact topological space, there everything will be there, every four condition of all the three condition will be there except the one for which the denseness is there. So that condition need not necessarily satisfied. Okay, if there is any doubt, please ask, otherwise I'll do the next question and I will do few more minutes. I think this is the question number 9. No, not this one. Question number 9. Here is the question number 9. Yeah, this is the question number 9. This is the question number 9. Okay, so what question number 9 says that consider the equivalent relation on a closed interval 0, 1. Okay, which is that, what is the equivalent relation? That consider equivalence relation, consider equivalence relation on closed interval 0, 1 by x related to y if and only if either x is equals to y or x and y are can be 0 or 1. Okay, if x and y is one of them is 0 and 1, then they are related. So you can just you can think like this way, that 0 and 1 point are considering a single point. Okay, this is vaguely but not theoretically. 0 and 1 point are considering single point. So that means here 0 and 1 are considering a single point. Either 0 will be there or 1 will be there. So I can write this way. So in that situation, so this set is homeomorphic. Okay, so this is the idea. So 0, 1 is homeomorphic. The quotient space 0, 1 is homeomorphic. So this set is homeomorphic to, basically not directly this way, but this set is homeomorphic to S1. I think, yeah, this set is homeomorphic to S1. So we'll discuss how this set is homeomorphic to S1. We have to give a homomorphism. That is all. Okay. So if you recall the quotient topology, mainly quotient topology and the uniqueness of universal property of quotient topology. So now let's give a map. Let's f from give a map f from closed interval 0, 1 to S1 by f of t is equals to e to the power 2 pi I t. Then f is surjective. Check that. That is easy. You can take any point S1. Any point S1 can be written to the power 2 pi I t. So that's why you'll get the t from 0 to 1 closed interval. That is what. Okay. T from 0 to 1. You see, f is surjective. Now note that if x and y are coming from the interval 0, 1, 1, I mean either x is 0 or y is 1 or x is 1, y is 0, then f of t, okay, sorry, just let me write it clearly. If t is belongs to the set x and y is equals to 0, 1, if t belongs to the set 0 or 1, then f of t, t1 and t2 are two sets, then f of t1 is equals to f of t2. That means, and so that means this is all. I think this is all. That means f maps every equivalence classes of the closed interval 0, 1 to a constant function. Equivalent classes to a single fixed value, to a fixed value. What I am saying is that f is a map which maps every equivalent classes to a single value. How this is true? That just note that what is the equivalent classes? Equivalent classes are either they will be x and y are coming from 0, 1. Okay, so you can note that t1 and t2 are coming from the set 0 or 1. T1, T2 can anything. I mean, only 4 possibilities there. T1 and T2 both are 0. T1, T2 both are 1 and T1 is 0, T2 is 1. In that situation, f of T1, f of T2 are same, right? Because e to the power 2 pi I of 0, 1 and e to the power 2 pi I of 1 is again 1. Cos 2 pi plus I sin 2 pi, yeah, that is 1. So that means they are same. And whenever x and y are same, then obviously f of x is equals to f of y, there is no problem. So that means f is the function which is constant on the equivalent classes. That means f is constant on the equivalent classes. That means f is constant on the equivalence classes. Then we know pi, from pi the usual surjective map, pi from close interval 0 1 to close interval 0 1 mod this equivalent classes, which maps pi of x to the equivalent class, right? Then each surjective continuous map with respect to quotient topology of this 0 1 mod this, and any continuous function f from 0 1 to a set S1 or any set, here any set, must factors continuously through 0 1 mod this one. So that means there exists, there exists a continuous map f naught, there exists a unique continuous map, there exists unique continuous map f naught from 0 1 close this to 0 this to S1 such that following diagram commutes. That means suppose I have the set x is equals to 0 1, okay, here x is equals to 0 1, and I have automatic surjective homeomorphism, surjective map from 0 1 to this one pi, and suppose I right now I have a map, another map S1, this f, and f is constant on equivalent classes, constant on equivalent classes. So now what so my point is that there exists a unique continuous function f naught such that f naught compose pi is equals to f. Okay, this is continuous and unique, and note that, so also note that the way f naught is defined for this, I'll refer, look at the lecture notes, look at the lecture notes, which lecture it is, it is I think 31 32 33, defined f naught is bijective and continuous. Okay, so why this is bijective I can simply say right now. First of all, the set here f is continuous. This f, how this f naught is defined, if I write now how this f naught is defined, f naught on a equivalent class x, what are the element in closed interval 0 1 mod this equivalent relation. So these are the equivalent classes like f of mod box x, box x is the equivalent classes. So f naught x is defined like f of x. This is the image. Okay, so now as f is surjective, for every point y in S1 there exists a point in closed interval 0 1. So that point y suppose that point is f inverse of y, and that point will map to equivalent classes like f inverse of y box. I will not write this one. Okay, I can write here. Okay, I'll write, at least I'll try to. How this map is defined. How this map is defined, if you know how this map is defined, then it is clear. Okay, so here you have 0 to 1. And suppose you have pi 0 to 1 mod this equivalent relation. And suppose you have S1. And if this F, this is surjective. Okay. Now, if you want to, and continuity will be automatically coming from the F. There exists unique F naught. How this F naught will be defined? Suppose I have taken how this F naught is defined, that equivalent classes will go to the f of x. If I take an x here, there should exist equivalent classes mod of x, or every equivalent classes there should exist a representative from the closed interval 0 1. So now, so that 0 1, suppose if I take an equivalent classes here, there should exist a representative here, and that representative will be mapped to S1 by F. So this is the map how it is defined. Okay. Now suppose you have, now I will prove that this F naught is surjective. This F is surjective. So for any y belongs to this particular set, for any y which is belongs to this set, y will be, there should exist an F inverse of y, right? Now because F is surjective, now this F inverse of y will be mapped to a point here, F inverse of y box, that is equivalent relation. So that point will be mapped to here. I mean that map, that will automatically, you can look at this, this will be like f naught of f inverse of y, this box, equivalent classes, that will be y. So that means f naught is surjective. For every point y in S1, I am getting an image there. Okay, and that is for sure. That is no problem actually. F naught of f inverse y will automatically map. This box will be like f of f inverse of y. F inverse means this is inverse image. Okay, so that means this is y. Okay, so 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 this is the f node will be surjective, first condition, and f node will be injective. Why f node will be injective? Because equivalent classes are mapping to the, and you can check f node is injective. F naught will be injective, something like this. You can look at this way. Let's take x and y 2 point. Okay, in the closed interval 0 1 mod this one. Okay, suppose these are two equivalent relation. Now if f naught of box x is equals to f naught of box y, that means f of x is equals to f of y. But when this is happening, either x is equals to y, or x and y are sitting inside this 0 1 set. But in any way, if x satisfy any one of the condition, x box is equals to y. So that means f is injective. So I can write this one as the rough. So that means f naught is injective. F naught is injective. I think this is clear. If I take 2 equivalent classes in closed interval 0 1 to this relation, then f naught of box is equals to f naught of y. So that means here, just 1 minute, one more minute. So f naught of box is equals to f naught of y. That means f of x equals to f of y. That means either x equals to y, or x and y are closed interval, are in the either 0 or 1, not closed interval, 0 or 1. X and y are in the set of 0 and 1. So that means in any way, if x and y are satisfy this condition, then x and y are their same equivalent classes. That means this is injective. F naught is injective. So main point is that f naught will be bijective continuous function. Okay, but just 1 more minute. But as pi from x to, not x here, 0, as pi from 0 1 to 0 1, this one is continuous and surjective, continuous surjective, then pi should map compact set 0 closed interval to the compact set 0 1, which is, what is this? This is equals to 0 1 relation this. So this set is compact. So this is compact. So that is what? That is what I am saying. Okay. So that means, and also note that S1 is housed off. Okay. So F naught from this 0 1, this one to S1 is a bijective continuous map from a compact set to a housed off space, then F naught is homeomorphic. That means S1 is homeomorphic to 0 1. So so what are the question that this is the question space 0 1 is homeomorphic to S1, and S1 is not homeomorphic to none of this. None of this. S1 is, and as S1 is not homeomorphic to, so A is correct, and S1 is not homeomorphic to 0 1 open interval, close interval 0 to 1, and 0 open 1 closed. So B, C, D are not correct. Okay, I will stop here. I will do the next last three problem in the next Tuesday's class. So till now, is there any doubt? You can ask. If there is no doubt, I will stop them. Is there any doubt? It is paused due to the. There is three more problem that I will do in the next class. What are the three more problem? That is 10, 11, 12 that I will do in the next class. So if there is any doubt, please ask. Otherwise, I will stop here. Okay, I am supposing that you don't have any doubt. If you have any doubt, please ask in the next class. So I will stop here. Thank you.